Hi, now we are solving CSIR Net December 2015 Chemical Sciences. Just look at the given problem. Mass bar spectrum of a metal complex gives the information about acceleration state and spin state of metal, types of ligands coordinated to metal, nuclear spin state of metal, and geometry of metal. Okay, just check the concept lecture on mass bar spectrum in your course, and here for this problem, the mass bar spectrum of a metal complex gives the information about acceleration state and spin state of metal, and types of ligands coordinated to metal, and also gives the information about geometry of metal. Okay, for example, if you take iron complex, okay, here we have taken iron Cl6 and another one is iron Cn6. Okay, so by just changing their acceleration states. Okay, so in that condition we may observe based on symmetry of the given complex and the symmetrical distribution of electrons in the d orbital of particular metal, we may decide acceleration state, spin states of metals. Okay, here spin state of metal is just based on the type of ligand which is coordinated to the metal. Okay, so that also defines the particular line, mass bar spectrum line for the particular given metal complex. Okay, for example, if the given octahedral complex of iron is in perfect octahedral in structure, at the same time if it is having equally distributed or chemically equivalent electron distribution is present in its d orbital, okay, that means in T2J and EG levels, then also it gives only one signal due to the absence of quadrupole splitting. Whereas if we get any one of it, that means if the symmetry of the particular metal complex or if electron distribution in its d orbital or non-symmetrical, okay, in both of them, if one is non-symmetrical, then it leads to the quadrupole splitting and it gives doublet or two signals in mass bar spectrum. So that's why here that information gives total acceleration state, spin state of metal, and type of ligand which is coordinated to metal, and also it giving the information about geometry of metal. That's why here our option 3 is the correct answer. Okay, right. So here it doesn't give the information about nuclear spin of metal. Next one, for the uranocene, the correct statement or statements are here. Acceleration state of uranium is +4. It has cyclooctatetraenide ligands and it is a bent sandwich compound. It has -2 charge. Okay, just observe this is the structure of uranocene, and where uranium is having 2 cyclooctatetraenide ligands. Okay, so which is sandwich compound, but it is not bent sandwich compound. That's why option C is simply eliminated. And just observe uranium here. Uranium, so each cyclooctatetraenide. So if you know the IUPAC names and if you have the command on IUPAC name, and you can check that cyclooctatetraenide, that means it is having -2 charge. Okay, enide. Okay, that's simply indicating presence of -2 charge in cyclooctatetraene. Okay, so that's why each of it containing -2 charge. That's why uranium should contain +4. So here -2 and here -2. That's why uranium contains simply +4 acceleration state. Okay, and it has cyclooctatetraenide ligands. So that is also correct one. And acceleration state of uranium is +4. That's why simply option A and B is the correct answer. Okay, right. The final products of the reaction of carbonyl metalloids like vanadium and cobalt complexes are given, carbonyl metalloids are given, and which are reacting with phosphoric acid respectively, and that means the final products we need to find the reaction of phosphoric acid with the 2 vanadium and cobalt carbonyls. Okay, right. Here just observe the reaction here. Vanadium, if we observe the vanadium complex or carbonyl here, just we need to check its electron, total electron. That means is it near to 18 electron? It is 18 electron or less than or more than that. If it is having 18 electrons, then we know that it is stable one. Just observe here, vanadium complex is simply containing 18 electrons with that extra electron on vanadium. Okay, so here vanadium is having 5 electrons. That means valence shell having 5 electrons because its D contribute 3 electrons and S contribute 2 electrons. So total 5 electrons. And if you look at the complex is having negative charge on it, so we need to add another 1 electron. So total 6 electrons from vanadium, just think like that. And from 6 CO ligand, each CO ligand contribute 2 electrons. So 6 into 2, 12 electrons. So 12 plus 6, total 18 electrons for it. That's why whenever we add phosphoric acid, simply it takes proton from that protic acid. Okay, we know that H3PO4 is a protic acid. That's why it donates its H plus, and here is the final product. Okay, so which is also having 18 electrons. We have total 18 electrons in this reaction. Now if you look at the cobalt carbonyl, and here if we count the total electron counts, it simply equals to 17 electrons. Okay, add the extra electron to it, that's why it becomes 17 electrons, and it needs another 1 electron to become stable. Okay, so that's why whenever it takes in or it reacts with phosphoric acid, it doesn't easily takes its proton, but it dimerizes to produce CO2 CO8. Now just observe, due to the formation of metal-metal bond between two CO, okay, due to the formation of metal-metal bond, then the total electron count equals to 36. So this is effective atomic number. Okay, 36 electron count is simply equals to krypton. So that's why it is effective atomic number, that is stable electrons. That's why here this complex is stable. That's why the cobalt complex or carbonyl dimerizes to produce this complex. Okay, now just check the two products in the options, and that is our answer. Okay, right, next one, the correct statement about the substitution reactions of cobalt complex with OH minus ion to give the particular product. Just observe it. It obeys first order kinetics. Its rate is proportional to the concentration of both the reactants. It follows the SN1CB mechanism. Its rate is dependent only on the concentration of OH minus ion. Okay, here we have given with simply base hydrolysis of the particular cobalt complex. Okay, in the first step, slow step. Okay, the first step is a slow step where the dissociation of 6 coordinated cobalt complex takes place, and it produces 5 coordinated intermediate of the particular cobalt. Okay, in the next step, the fast step, where base OH minus ion and attacks as a nucleophile, and that is the final product which is given in the problem. Okay, so that's why if you observe this reaction here in this base hydrolysis reaction, the rate determining step is the first step where dissociation of the substrate is taking place. That's why the rate determining step, or the rate is simply depending on the substrate, not on the base. Okay, then now just observe, it obeys simply first order kinetics, because rate of the reaction depends only on the substrate concentration, not on the base concentration. That's why it is obeying first order kinetics. Now second statement, just look at it. Its rate is proportional to the concentration of both the reactants. It is wrong statement, because the rate is only depending on the substrate, but it is not depending on the other substrate, that is here base OH minus. That's why second statement is wrong. And if observe third one, it follows the SN1CB mechanism. Now if you look at the given substrate, the substrate doesn't contain any protons in it. For example, it contains ammonia as ligand, then there is a possibility to abstract the proton from that NH3 by the base, then there is a possible mechanism of SN1CB. But the substrate doesn't have any protic ligands on it. That's why the third statement is also wrong statement. Fourth one, its rate is dependent only on the concentration of OH minus ion. This is also wrong statement, because it doesn't depend on the concentration of base, it only depends on the concentrations of a particular substrate complex. Okay, right. So here just observe the correct statements for it. Okay, right. Now aqueous chromium plus 2 affects one electron reduction of the given cobalt complex giving compound Y. Compound Y undergoes rapid hydrolysis, then Y is, we need to find. Okay, here just observe the cobalt complex is reacting with chromium plus 2, and if you look at the given cobalt complex, it is having chlorine. So whenever we just look at the presence of chlorines, that means halogens, then there is a possibility of inner sphere transition. Okay, the reaction takes place inner sphere transition. Now whenever the chromium aqua complex react with it, there is a formation of bridge with the chlorine. Now the electron from the chromium goes from the chlorine to cobalt. Okay, so here cobalt is having d6 electronic configuration and it is inert complex, and after electron transfer from chromium and where the chlorine is acting as bridge to transfer that electron to the cobalt, now cobalt complex is become labile with d7 electron and the chromium complex becoming inert. Okay, so these are the some features of inner sphere mechanism, where inert and labile complexes are convert their natures during the reaction, and inner sphere mechanism contains bridge. Okay, so here chlorine is acting as bridge in between them, and in the next step we can get the final product by following hydrolysis. It produces the cobalt aqua complex. Okay, just observe it. Next one, the reaction of BCl3 with ammonium chloride gives product A, which upon a reduction by sodium borohydride gives product B. Product B upon reacting with HCl affords compound C, which is, okay, in the first step, whenever boron trichloride reacting with ammonium chloride, it forms just like non-benzene, okay, inorganic benzene. So with substitutions of chlorines on each atom, that means boron, nitrogen. Okay, just observe the structure here, and that is A, compound A, and whenever it reacts with sodium borohydride, simply the reduction takes place by the elimination of chlorine. Just observe, and then the final step, whenever it reacts with HCl, so here in nitrogen gets H plus and boron gets Cl minus. Why? Because just observe, here we have shown the arrows, that means coordinated bond. Okay, that means electrons, or that means lone pair of electrons on nitrogen are giving to the vacant orbital of boron here. That's why the arrows are towards the boron from nitrogen, right? And whenever we add HCl, here the lone pair of electrons on nitrogen attack on H plus, and whereas Cl minus ion attack the vacant orbit of boron. That's why here boron gets chlorine and nitrogen gets hydrogen, and this is the final product. Okay, that is simply option 1 is the correct answer for it. Next one, the number of valence electrons provided by a ruthenium, just observe fragment. So carbonyl fragment towards cluster bonding is. So here we need to find total valency electrons for that ruthenium carbonyl. So that is equals to here is the formula. Total valence electrons equals to 18x minus 2y, and here we have only one ruthenium metal in the place of x. So y equals to metal, the number of metals. So y is equal simply equals to 2. That's why here the fragment ruthenium fragment, the number of valence electrons provided by this ruthenium fragments equals to 2 to form a cluster. Okay. Next one, choose the correct statement about the Tanabae-Sugano diagram. Here we have given with the E by B is plotted against delta 0 by B. The zero energy is taken as that of the lowest term. The terms of the same symmetry cross each other. Two terms of the same symmetry upon increase of ligand field strength bend apart from each other. We need to find correct answer. Okay, and just look at the Tanabae-Sugano diagrams. That means already we have discussed in our course. So just check the concept video on the particular Tanabae-Sugano diagrams. Okay, right, whatever here, just look at the first statement. E by B is plotted against delta 0 by B. This is the correct statement according to Tanabae-Sugano diagram, and the zero energy is taken as that of the lowest term. This is also correct one. And terms of the same symmetry cross each other. This is the wrong statement, because just observe the Tanabae-Sugano diagrams. Whenever the terms with same multiplicity, okay, same symmetry, just repel each other. Okay, they repel each other and they never cross each other. Okay, in the orbital diagrams, in the tanabae-sugano diagrams also. Okay, just check them. That's why here the statement C is wrong. Two terms of the same symmetry upon increase of ligand field strength bend apart from each other. So this is the correct answer, because whenever that happens, this two same symmetry containing lines just move apart. Okay, so they repel each other. Okay, they never cross each other. So that's why here our simply just check the answers here, A, B, D. So that's why 3 is our answer. Okay, right. Next one, which of the following statements are true for the lanthanides? The observed magnetic moment of europium plus 3 at room temperature is higher than that of calculated from spin orbit coupling. Lanthanide oxides are predominantly acidic in nature. The stability of samarium 2 is due to its half-filled subshell. Lanthanide ions can be separated by ion exchange chromatography. Here we need to find the correct statements regarding the lanthanides. If you observe the first statement, the observed magnetic moment of europium plus 3 at room temperature is higher than that of the calculated from spin orbit coupling. So this is the correct statement. The calculated values are not equal to observed values for europium plus 3 and samarium plus 3, because due to the small spin orbit coupling, that is nearly 300. Okay, so due to that, the observed magnetic moment of europium plus 3 at room temperature is higher than that of calculated one. Okay, from spin orbit coupling. Now, so that is the correct statement regarding the lanthanide. And here lanthanides oxides are predominantly acidic in nature. This is the wrong statement. Lanthanide oxides are basic in nature. Okay, alright. The stability of samarium plus 2 is due to its half-filled subshell. This is a wrong statement, because if you observe samarium plus 2, it contains 4f6 electronic configuration. That's why it is not half-filled. That's why the statement C is wrong statement. Now, if you look at the fourth statement, lanthanide 3 ions can be separated by ion exchange chromatography. This is the correct one, because we know that lanthanides are having similar size. Okay, due to the lanthanide contraction, almost they are all having similar size. So due to the similar size, it is difficult to separate from chemical methods. Okay, that's why here we need to use ion exchange chromatography. Okay, that's why fourth statement is also correct one. Only here B and C statements are wrong. Okay, that's why here option 1 is the correct answer. Next one, the intermediate and final major product of the photolysis of Z. Here this is Z, and we need to find the correct reaction here, intermediate and final product. If you look at the first Z here, reactant, and here we need to check its electron count. Okay, that is very important. Just remember, whenever we are given this kind of problems, first we need to check the stability of particular metal complex. Okay, then only we have a particular idea on that particular complex, how it's going to react. Okay, so that's why we need to check it. That's why it is better to check their total electron count on the particular metal complex. And if you do that, the metal complex is having 18 electrons. And the next step, under photochemical condition, one of CO just eliminated from it, and this is intermediate, which is containing 16 electrons. We know that CO contribute 2 electrons in it. That's why whenever one CO is eliminated, then the intermediate contains only 16 electrons. Now it needs 18 electrons to be stable. That's why here is a formation of allyl. Okay, that is neta 3. So here it contributes, the total electron count here equals to 18 electrons. Okay, so this is the intermediate, and this is the final product. Okay, right. Next one, reaction of Mn2CO10 with iodine results in A without loss of CO. Compound A on heating to 120 degrees centigrade loses CO ligand to give B, which doesn't have a manganese-manganese bond. Compound B reacts with pyridine to give 2 equivalents of carbon. Compounds A, B, C from the following respectively are. So if you look at all the questions which I have seen in this video, all are given with lots of information for the particular inorganic problem, okay, but they are having simple answers. So that's why don't be panic whenever look at this kind of problems with lot of information in it, okay. So just read the question clearly and observe and pick the important information from the particular problem, then the answer will be very easy for those kind of problems, okay. And for this problem, answer is very easy, because just observe the given 5. So here we have given it 5. So 5 compounds of metal complexes. So we need to check the A, B, C. From that we need to pick A and B, A, B, C. First thing, whenever you locate the given manganese carbonyl, which is given that means dimer, okay, right, and reacting with iodine, result A without loss of CO. That means there is no loss of CO here, but here is also we need to check for the stability of the complex. Now if you count the total electron count on this manganese complex, it is simply equals to 36, okay. That is effective atomic number, the stable atomic number, okay. And whenever it reacts with iodine and it gives some product, it should also be stable. Now whenever it reacting with iodine molecule, then the second compound should be the correct one. Just observe it. So manganese with 5 CO ligands and 1 iodine ligand, it result 18 electrons. That's why stable species produced from it, okay. So this should be the first one. Now compound A on heating to 120 degrees centigrade loses its CO ligand to give B, which doesn't have a manganese bond. So just observe, option A is having manganese bond, that's why we can eliminate it, and the second one also eliminate, because already we have find that second compound as A, okay. Now we have these 3 compounds, okay. In that, just look at here, if you look at the third one, it is having pyridine in it, but there is no possibility of pyridine in the reaction of first complex with iodine and in the next heating it. So that's why we can also eliminate this one, and here we have only these 2, okay. And in that we have a clue that there is no metal bond, okay. There is no manganese metal bond. And if you look at the fourth one, it is also having pyridine. That's why it is also not possible, because the pyridine ligand is not there in the initial reaction of that particular manganese dimer, okay, carbonyl, okay. That's why the next B must be fifth one, okay. Just look at it, how easy it is when we understand the problem, okay, right. Now this is the B. Now we have to look for C compound here. To give B, which is doesn't have a manganese bond, and compound B reacts with pyridine to give 2 equivalents of C. That means whenever this going to reacting with pyridine, it must give 2 equivalents. That's why here is the breakage should be there between the 2 complexes. Whenever it happens, 1 iodine 1 pyridine for one complex and 1 iodine 1 pyridine for another complex, and which are chemically equivalent, okay. So that's why here that must be fourth one. So here just check the answer. The first one is the answer for the given problem. So here just if we observe the given problem well, and if we look at the problem with concentration, then we give answer with ease, okay. There is no difficulty in it, just we need to find the find from the given options, okay, right. Thank you.